Okay, so in the previous segment, we saw the need for constitutive relations, or at least what we said a priori we are going to call constitutive relations. Let's get into this business now. For this development, it turns out that perhaps the most convenient way to approach it is to just write out our equations and then start out from there. Okay, so let's look at, so we're going to study now constitutive relations, or at least we're going to start studying constitutive relations. Okay, and let's look at the balance equations that we have. Okay, I'm going to write everything in the current configuration. So we have partial of rho with respect to time plus gradient of rho dotted with the spatial velocity plus rho divergence of the velocity equals 0, right? Our balance of mass. And we also have our balance of linear momentum, right? We have rho, partial time derivative of the spatial velocity, plus the convective term, right? All of that makes up for us our material derivative of the spatial velocity, and this is divergence of sigma, divergence of the Cauchy stress, plus the body force. Okay, and both of those we recall hold in omega t cross the time interval. All right, now it turns out that because of the way we've written out these equations, it is most convenient to use as a stepping off point fluids, okay, to discuss things. So let's consider, okay, so let's consider for fluids, okay, so for fluids, right, and those of you who think only of solids, worry not. You need to know what a fluid is to know what a solid is not, so that you know what a solid is. Okay? So we study fluids. Okay, so for fluids, let's start out with this notion of an ideal fluid. Okay? So an ideal fluid is one in which we say that the stress is equal to some scalar, okay, that I'm going to denote P very suggestively, times the isotropic tensor. Okay? Should be obvious why we call this an ideal fluid. When you study an ideal gas in the context of thermodynamics, we think of an ideal gas as something that only bears pressure, and indeed the P is the pressure. Okay, so we think of P as being the pressure. Okay, and it's an ideal fluid in the sense that it's also the same at every direction, right? The stress tensor, right, which we know has this intrinsic sense of direction also in it, right? Turns out to be the same in all directions because, of course, it's multiplied by the isotropic tensor, right? The second order isotropic tensor. Okay, so let me just say this: the stress is same in all directions, and we will use the proper mathematical term for it, which is isotropic. Okay? Of course, this, well, let's check now. Does this help matters? So what we have done is, by doing so, by writing out the Cauchy stress in terms of the pressure, we have effectively introduced 6 extra equations. Right? And this is a good thing because 6, as we know, equals 10 minus 4, right? 10 was the number of unknowns that we had when we counted up unknowns, and 4 was the number of equations that we had when we counted up the balance laws alone, right? So if you look at this form that I have on, at the top of the slide, those two balance equations involve 4 equations, right? And 10 unknowns, all right? And so now we've got that difference, right? Well, yes, but are we saved yet? Obviously not if I pose it in that manner. And the reason is we have an extra unknown now. What is P? Okay? Okay? So we need to say something more, right? We're not out of the woods yet. So, and that takes us on this journey of looking at types of fluids. Okay? The very first case that we will consider is that of an incompressible fluid. And maybe I should title this by indicating what we're trying to do here. Okay, so P is determined by what you may think of as the constitutive relation for the fluid. Okay, and so we embark on a short journey through types of fluids. Okay, the first that we will consider is what we call an incompressible fluid. As the term indicates, this is a fluid that maintains its density. Okay, so even though we're talking about fluids, and really the natural way to describe fluids is in terms of the spatial configuration, right, where we have a basis, but really we're looking at a point in space. You're looking at that window here, right, and you're just looking at the fluid going through it, right, and therefore we always measure the fluid density at that point in space, right, at that window, right. Now, however, what we can take advantage of is the fact that, well, yes, we know that this we measure a density only at a point in the fluid, only at a point in space, but we have this notion, at least this mathematical notion, of the density with respect to the reference configuration, right? Whatever the reference configuration was. In the case of a fluid, which is just flowing past our window, we don't really, it's a very difficult job to actually track back where all those particles came from. Okay, nevertheless, they exist, right? That other configuration does exist. Okay, so for incompressible fluids, what we say is that rho, function of x and time, equals rho 0 at some position, reference position that we don't know. That's all, right? That reference density does not depend upon time. Okay, right? What this implies then is that since we have this, we know that the material derivative of the spatial density, which is this, right? And we've shown why it is this, is also the same as the material time derivative of the reference density, which, however, is a function of position alone, right? And this is therefore dead zero. Okay? And then we say that, well, for an incompressible fluid, the pressure is whatever it needs to be in order to satisfy this condition. Okay? Now we note that this condition gives us it can be simplified further, because if we apply this to our balance of mass in the current configuration, okay, so what happens then with our balance of mass is okay, we have the balance of mass was partial time derivative of rho plus the convective term plus rho divergence V equals 0. What we've just shown above is that for an incompressible fluid, this is equal to 0. And so it is that incompressible fluids have this condition, divergence of V equals 0. Okay? And then their balance of momentum, right? Linear momentum becomes rho the material time derivative of the spatial velocity equals now divergence of sigma, right? But sigma is equal to P isotropic tensor, right? Plus body force. When you substitute the fact that sigma is equal to P isotropic tensor, P multiplied by the isotropic tensor, what you get here is the gradient of P, okay, plus BF, right? Okay, so the equations that we have are 1 and 2. Okay, and now if you count, and we know that these equations add up to 4 equations actually, because the second equation is actually 3 of them. But how many unknowns do you have here? Right, so we know here that equations are 4, unknowns are 4. Okay, velocity and the pressure. Okay, so our system is closed. And the way we've done this is by specifying an additional constitutive assumption on the fluid. Our constitutive assumption is the title of this type of description of fluid, which is that the fluid is incompressible. Okay, so that gave us an additional condition which we put into the balance of mass to simplify it. Okay, effectively what we've done is to eliminate the density. Okay, we no longer need to solve for the density. That would come to us from an initial condition. Okay, so that's the case of the incompressible fluid. Let's look next at what we call a compressible fluid. Oh, perhaps before I do that, okay, we will look next at a compressible fluid, but I just ought to mention that the equations we ended up with, the equations that I've numbered 1 and 2 on the previous slide. Let's see if I can go back here for a second. Yeah, the equations I've numbered as 1 and 2 essentially add up to the so-called Euler equations. Okay, so equations 1 and 2, as I've labeled on the previous slide, are the Euler equations for a fluid. Okay, the second type of fluid that we will consider is a compressible fluid. And this one is fairly straightforward. What we say is that yes, I know that we have this extra variable P, but let me just say that P is some function of the density. Okay, so we've applied closure. We have not introduced any new unknown because the density was already an unknown, right? And of course, we're talking of a compressible fluid, so we're not saying that the density stays fixed at the reference density. Okay, so now if we write out the equations, what we have is the following, right? We have okay, and our balance of linear momentum. Now, just as we had on the previous, for the previous case of the incompressible fluid, we have that the divergence of the stress does reduce to gradient of P, okay? However, P is a function of rho. Okay, so it is really just the the gradient of some function of rho. Okay, no new variable, no new unknowns. Okay? All right. And so again, for the unknowns, we have 4, right, which are now rho and V, and equations are 4. So in this case, the equations and unknowns are add up to the same number, so again we have closure for this system. These are also the Euler equations. However, these are the Euler equations for a compressible fluid, right? So these are called okay. Now, let's continue working with this idea. This idea which was just introduced, that we can write the pressure and therefore effectively the stress as a function of rho, right, as a function of the density. And let's do that by observing that sigma equals P, it's a function of rho, times this can also be written as P. Now, we can write the density, right, the density in the current configuration as rho naught over determinant of F, right? And we demonstrated that there was this relation between the density in the current configuration and the density in the reference configuration, okay? All of this times the isotropic tensor. So this gives us an inkling that, oh, we have a relation between sigma and the deformation. Okay? We're talking about a fluid here still, but as we relate sigma to the deformation gradient, actually, it introduces us to this notion of a fluid that has some sort of elastic behavior in it, right? So this fluid that we have, I can't quite hold it in my hands, but in my fingers. But you know what I'm saying is that, look, I'm trying to squeeze this bottle, right? I'm going to squeeze it without introducing any kinks in the bottle. Anyway, see, I'm squeezing the bottle, and what is happening is that to some very small extent, the fluid is being squeezed, right? The water is pretty much nearly incompressible at the kinds of stresses that I'm able to impose upon it, right? However, there is a little bit of a change in of course, there's a change in the determinant of, in F itself, okay? There may even be some amount of a change in determinant of F here. Right? So if we're saying that, yes, we are able to change the volume of the fluid, right, as we're deforming it, it introduces us to this notion of an elastic fluid. Okay? So this is an elastic fluid. Okay? Turns out that if you treat polymer melts, all right, they often need to be treated as elastic fluids. What this also brings us to is the following idea, right? If we look at the fact that we now have sigma equal to the pressure, which depends upon the current density, but then we're saying that the current density is parameterized by position and time. Okay? right? And we have this. So what we're saying ultimately is that the stress in this body depends upon the position of this point in space at which we were talking about the stress, and it depends upon the current time. Okay? So it depends upon the position right here and the present time. Okay? This may seem very obvious, but it's not necessarily so. It is a principle of constitutive theory that is called the principle of local action. Okay, that the stress at this point depends upon that point only, right? What's happening at that point. Okay, and it depends upon the current time. Okay, not time past. Okay, so stress depends on current position of particle of interest and current time. Okay, and this is what is called the principle of local action. It's a principle, right? It is not a fundamental requirement, it's not a theorem, other things are possible. Okay, we're applying a principle of local action here. Okay? Also, I should mention that we're working in the context of fluids, but just remember this relation, okay? That sigma is related to F. It's something that you may already expect we're going to return to in the case of solids. Okay? To round off this discussion, I want to just talk about non-ideal fluids. So far we've been talking about ideal fluids, whether compressible or incompressible, in as much as that the stress depended on the pressure and it was isotropic. Okay? So let's now look at non-ideal fluids. Okay? Where the idea is that the stress, okay, maybe it does depend upon the pressure, and the pressure may be a function of the density or not, but there is more. Okay? I'm going to in general denote that as sigma sup V, because the most common example of a non-ideal fluid is a viscous fluid. Okay, and we know that of course most fluids are viscous. Pretty much every fluid is indeed viscous. Okay, so this is often referred to as the viscous stress. Okay, and the form for this is that we have sigma V is a function of the spatial velocity gradient. Okay, and this idea also comes from the fact that if, okay, once again we have this fluid, but if you were to take it in a bucket or in a tub, or you try to move your hand through it, the fact that you're setting up the spatial velocity gradient in the fluid offers a resistance to the motion of your hand, right? And that is the viscous response of the fluid. Okay, the fluid creates a stress because it feels a spatial velocity gradient, and that stress is imposed upon your hands. Right? Or another very common experiment that many of you may have done at some point is the so-called parallel plate experiment, right? You have a plate, which is the top thing I'm drawing here, okay? And we move it at some velocity, right? What we see here is at the bottom, the velocity is 0, okay? And here we have V equals V naught, right? If that distance is L, okay? So there's a velocity gradient set up here, and the magnitude of the velocity gradient here can be written as the magnitude of V naught divided by L, okay? And what is found is that if you try to move this plate, you need to move it with a stress, okay? And I'll just write that as sigma V. I'm just writing it as a scalar, sigma V, okay? All right? That stress would be equal then to the force that you would have to apply upon that plate divided by its area, okay? And the relation that's usually found is that sigma V, which is the force you need to apply, divided by the area of the plate, is often equal to the viscosity of the fluid times V0 over L. Okay? All right? So this is the simplest sort of example of a viscous fluid. So it's also called what we call a linear viscous fluid. Okay, we'll get into those details later, right? But the basic idea is that we have this type of relation. Okay, so this is our first example of a non-ideal fluid. It's also a good place to stop this segment. When we come back, we will talk in more detail about this idea of a viscous fluid, and we'll invoke other details of constitutive theory to further elucidate this particular function that I've circled at the very bottom here.